Hi, welcome to lecture 16. Today we're going to talk about the equations, the Dirac equation and fermions. Historically, Paul Dirac was motivated by searching an equation that is linear in the derivative operator because he thought that it was that caused problems with quantum mechanics and special relativity. Today we know that it is not exactly the case, or it's more the single particle interpretation that breaks down. However, his search led to a new equation starting from the Glenn-Golden equation. He found a new equation that indeed described fermions such as the electron and other building blocks of matter. So let us look at the logic that he was using in the original derivation. And the basic idea is that Paul Dirac was trying to write the Glenn-Gordon equation as a product of the Glenn-Gordon operator as a product of two operators that one could separate and so derive a linear equation linear in the derivatives. Could it be done? That was the unknown question. And the problem is that the square root of the square of this vector derivative operator, which is a Minkowski vector product, is not really defined. So what is it? So what kind of new object can we find that would behave as a square root, more or less a square root of this operator? Well, and Paul Dirac came up with the idea to introduce a new type of vector. Let's call it gamma mu, with a subindex mu that runs over for the space-time indices. And it needed to have certain properties. For example, the zeroth component squared had to square to 1, and the spatial components had to square to -1. And also for different indices mu and nu, the sum of the swapped elements should give 0. And the shorthand notation for this expression, for this sum of the swapped components, it is denoted with these curly brackets. It's called the anti-commutator, right? The commutator would have a negative sign here. The anti-commutator has a plus sign. So the jargon is that one says that those objects anti-commute, yeah, if this anti-commutator is 0. So to summarize those requirements, that this zeroth component squares to 1 and the spatial components to -1 and the off-diagonal components anti-commute, we can write these requirements all together in a simple notation that the anti-commutator of those two vectors is equal to twice the Minkowski metric eta. Well, now you can multiply or contract this new vector with an arbitrary vector. Let's call this new arbitrary vector A for arbitrary. And there's also notation. This contraction with a gamma vector is called the slash notation. So you just draw a strike through this vector and call it A slash. And it's a useful shorthand notation because in Dirac type equations this kind of contractions appears quite often. Now we can check what happens if we take the square of this A slash square vector. We can write it explicitly in components, separating the zeroth and the spatial components. So we get the zeroth component squared and the spatial component squared, and then the cross terms of this type are like that. But we can anti-commute, so we can flip the gamma 0 and gamma I and pick up a minus sign here, which then cancels the other cross term that comes from the other multiplication of gamma naught, A naught and gamma I AI. So those terms are gone, and we're only left with this A naught squared minus AI squared, because this squared is 1 and this squared gives us minus 1. And that is nothing else than the a mu contraction with itself, which is what we wanted to achieve, because then a slash is morally speaking the square root of the a squared vector in Minkowski space. Now we can write again the Klein-Gordon equation, and the split as Dirac wanted is now achieved with the d mu gamma mu contraction, and we write gamma d slash here. So now the operator, right? So we can pick one of the operators to be satisfied in order to get a new equation. And let's pick the branch with a plus I m term. So we get d slash my plus I m psi equals to 0, or multiplying by I, we get I d slash minus m, which is a new operator. I could call it the Dirac operator acting on psi is equal to 0. And in momentum space, as you know, as we found actually in momentum space, the derivative operator is just equal to the negative I times the momentum, or the momentum operator. So writing it in the momentum space, we will have p slash minus m p slash minus m on psi is equal to 0, which is the famous Dirac equation. And now we want to discuss why it actually describes particles with spin. Let's see. Now we first have to figure out what are the components of the gamma mu vector itself. There are different representations, but we choose the convenient one, which is called the chiral or the Weyl basis. And in this representation, the elements of the vector are in fact 4x4 matrices. For example, gamma 0 is a 4x4 matrix where the off-diagonal block matrices are just unit matrices of 2x2 matrices, like this, 1, 0, 0, 1. And the gamma I matrices, the diagonals are 0, and the off-diagonal ones are the sigma I, which are the so-called Pauli matrices. Just a reminder from the quantum mechanics course, the Pauli matrices do indeed describe the spin. They are used to describe spin of particles, and the sigma 1 is given like this. It's a 0, 1, 1, 0 matrix, and sigma 2 is has the I, negative I here in the off-diagonal components, and sigma 3 is this kind of 1, 0, 0, minus 1 matrix. And the defining property for them is that their commutator is equal to 2 times I, the absolutely antisymmetric tensor sigma ijk times the sigma matrix itself, right? And this is absolutely antisymmetric tensor is equal to +1 if ijk are even permutation, if it's -1 if they're ikj, for example, is an odd permutation, like 1, 2, 3 would be +1, 1, 3, 2 would be -1, and all different possibilities. So it's essentially, yeah, a level 3 tensor. And of course, the properties of these Pauli matrices are that the trace of them, as you can see here, the trace of them is 0. Trace means that I sum the diagonal elements, right? The sum here is equal to the trace of the matrix, and it's obviously 0. Then sigma dagger, the transposition, if I transpose and complex conjugate the matrices, I get themselves back, so they are Hermitian. And they are related to the spin operator, as 1/2 times the sigma matrices is the spin operator, where this sigma matrix vector is just has 1, 2, 3, is a sigma 1, 2, 3 in its components. This is used to describe spin of a particle in quantum mechanics. And we see that it is indeed related to this Dirac equation. However, it is still even more complicated structures than just spin. It is essentially a double copy of particles with spin, and we will discuss this in a bit more detail now. So we can write this equation as gamma 0 p naught minus the gamma vector times p operator minus m epsilon psi, or in components it's really this kind of 4x4 block, and multiplying, of course, if it's a 4x4 matrix, to get the object it acts on is also a 4x1 vector. So we can write it as a vector with where we define the upper two components as psi L and the lower two components as psi R. Well, we see that if we can write this again in a shorthand notation as p naught minus sigma vector times p times pi psi L equals to m times psi R. So this, and the other version is p naught plus sigma times p applied to psi R is equal to m times psi L, actually. So this, yeah, we flip this signs here. Flip the components. So we see that the mass term actually couples the left, in the equations, couples the left type of fields with the right-handed fields in this equation, and vice versa. However, for m equals 0, those are completely independent, and we have two different equations for psi L and psi R components. And essentially, the theory completely splits in the theory in two theories of particles with that behave as particles with spin, as they are being acted on with the sigma matrices, and it's just a convention to call them left and right, and actually the convention is to call them left-handed and right-handed. As we will see in a little bit, they are actually related by the parity transformation. Well, now the massless equations can be rewritten using that P naught is equal to the energy, and it's equal to the absolute value of the momentum, since we have set the mass to 0. So then the equation simplified with this just being sigma p times psi L equals to the absolute value of the momentum times psi L, and vice versa for the psi R. There's an extra minus sign here. And now we can define the so-called helicity operator, where is the sigma times p, the momentum, the spin operator times 2 times the projected to the momentum divided by the absolute value of the momentum. So it's really a projection of the spin. So it's a projection of the spin on the direction of motion of the particle, and this is called helicity. Then we can see that the helicity operator acting on the left-handed fields gives us a positive sign, and the helicity operator acting on right-handed fields gives us a negative sign. But this is true only for m equals 0. So only for m equals 0, the psi L and psi R are helicity eigenstates. Are helicity eigenstates. Well, they are chirality eigenstates, but they're only helicity eigenstates when the mass is 0. If we have a mass, this is no longer true, and we can see it in a simple picture. So, for example, if we have here now the momentum projection, the spin projection and the momentum being in the same direction as the momentum, so it means helicity is +1. We can, if the mass of the particle is non-zero, we can always find a frame where we can overtake the particle, move faster than the particle, which would mean that the momentum shows in the opposite direction. The spin, however, is still pointing in the same direction. Now we have helicity -1 state. So chirality is not a helicity eigenstate if the masses of the particle are non-zero. So overall, the these equations can be used to generate a solution a specific solution for the mass equal 1, mass equal 0 case, and they can be generalized by a boost essentially to an arbitrary solution for the Dirac equation. So the solution of the Dirac equation has an exponential, the usual oscillatory e to the negative I xk term, like the usual plane wave solution. But the interesting structure here is that we have two types of so-called spinor functions that are multiplied by the plane wave solution, and they behave as, for example, the electron spinor has this 2 by 2 components that are, we can call them psi, for example, and they are multiplied by a momentum dependent factor p times sigma, that is the product of the momentum times the sigma matrix vector and taking the square root of it. And then we have a related vector, that is the so-called positron spinor, that is very similar, but it has a different 2 by 2 component here, and it is has a negative -1 sign down here in front of the second component. And this, one can show that this is the general solution structure of the Dirac equation. So for electrons, that would mean that having the substructure being having entries in the upper component of this 2 by 1 vector means that the electron will spin up. If it has an entry in the lower component, it is an electron will spin down. It is interesting that for this 2 by 1 vector for positrons, for the antiparticles of the field, the spin situation is exactly opposite. So 2 by 1 vector with a entry in the lower component is a spin up antiparticle, positron, and with an entry in the upper component, it's a spin down antiparticle. The spinors are normalized like this. U bar U is equal to 2 times m in the Kronecker delta S and R, where S and R are the spin spin indices here. So we could have, in principle, different spins of the particles, and they are normalized such they only give you something if they have the same spins. Same for the antiparticles, where the only difference that they have a minus sign, minus m2, 2m in their normalization factor. Now we just want to mention that this bar notation. The bar notation is actually the usual dagger operator of the spinor, so it's a complex conjugation and transposition here, which is has a shorthand notation of dagger, and then you multiply it by the gamma 0 matrix. Same for the antiparticle spinor V bar, and it is needed in such that this kind of combination U bar U is indeed Lorentz invariant, and this can be manifestly seen that this U bar U is just proportional to the mass, which is a Lorentz invariant quantity, is equal in all frames. Now let's talk about projecting out this kind of chirality eigenstates, right? Chirality, why chirality, comes from the Greek word chira, and indeed that is the case for our hands. Like a chiral object you can always look at is looking at your hands. They are mirror copies of each other, and so related by, as we will see in a second, the hands are related by parity, which means that we flip this space from x to minus x, all the coordinates. This is, and the same relates actually the eigenstates of chirality of the particles, psi L and psi R, hence the name. Now we are interested in projecting out those components. If we have a solution that has both of them and we want just to pull out the left or right-handed components, we can define the so-called gamma 5 matrix, which is I times the product of the other components 1, 2, 3, 0, 1, 2, 3, and is equal to negative minus the unit matrix, 2 by 2 unit matrix, and in the lower components we have a plus unit matrix, and the off-diagonal elements are 0, and or the block of diagonal blocks are 0. Now if we have let's call this psi minus, which only has the psi L component. If we apply gamma 5 on it, then we get the minus 1 out. So it's a eigenstate of the gamma 5 operator with a minus 1, and psi plus, which only has a right-hand component. If we apply gamma 5 to it, we have a plus 1. It's a plus 1 eigenstate of the gamma 5 operator. So we can define the projection operators by taking 1 minus gamma 5 over 2 and call it the left-hand projector, and 1 plus gamma 5 over 2 is the right-hand projector. And it's simple to see if you apply this left-hand projector to a state that has both L and R components, we get the same state from the 1, and then minus the psi L and plus the psi R components. So this minus psi L gives you a 2 psi L here, and then you divide by 2, and this 2's cancel, and this part here, psi R with the negative sign up front, psi R cancels this psi R, so the psi R component is gone. So applying this PL projector really pulls out the psi L state of an arbitrary state. Same with the psi PR projector, applying PR to an arbitrary state gives us just the right-hand component of it. Good. Let's see about some general transformation arguments. So in the general Lorentz transformation can be actually decomposed as in this exponential version as applying the boost by some boost to another frame. That's called the boost generator K, capital K, and a rotation that by some angle theta. Let's call the rotation generator J. Right, this negative I applies to both components, and then we have this kind of general Lorentz transformation. So how does this the generators behave under parity transformation, where parity flips the signs of space, right? Since if we have the coordinate system like this, after a parity transformation, the arrows point in the opposite directions. Here, let's say x, y, and z are being sent to the opposite directions. So that means also velocities are sent to minus negative velocities. However, that doesn't affect rotations, because they're symmetric in this space with respect to this inversion of coordinates. But since the boosts, you can really think, are dependent on the velocity, the boosts are getting a negative sign. So we need actually in our theory particles that transform with opposite signs under the boosts, kappa, okay, and those are exactly the psi L and psi R fields. And yeah, they are the eigenvectors of the parity operator with or no, they are not the they are not the eigenvectors. They are being transformed into each other by the parity operator P L and PR. P acting on psi L gives us a psi R, and P acting on psi R gives us a psi L. And in fact, valid representation in our basis for the projection parity operator is actually the gamma 0. So if we apply gamma 0 to a left-handed field, it becomes a right-handed field. Just a reminder now, or a useful fact, if you have, for example, terms that contain left and right-handed fields, products of them, so psi L bar, which contains gamma 0, multiplies a psi r, we have psi L dagger gamma 0 psi r is actually a right-handed field, and multiplying left-handed field and the gamma 0, which also makes it a right-handed field. So we have two right-handed fields being multiplied, which is non-zero, because you could say that they contain projectors that we defined here, the left and right PL and PR. So the right-handed fields you could write them as being a product of two right-handed projectors, and this is non-zero because the projectors are orthogonal. Their square is non-zero, but if we have a right-handed projector meeting a left-handed projector, this is really zero. And this happens if you have a psi L field with a bar, psi L bar, psi L, and psi R bar, psi R fields. You're actually multiplying left and right-handed projectors, which gives 0. So this contraction always gives 0 just because of the orthogonality of the left and right-handed projectors. So finally, we need to remember that chirality is the same as helicity only for the case when the mass is 0. So this is equal to the projection, helicity being the projection of the spin on direction of motion. But if we have mass, this was broken because mass couples the two parts of the Dirac equation together. And we, in our general solutions, we have two functions, spinor functions, that have independent 2 by 2 components that describe particles that can spin up and down, and those we have a 4-component in total. So the solution of the Dirac equation, a Dirac is a so-called Dirac spinor, has 4 degrees of freedom, and that corresponds to you could physically say that they correspond to an electron that can have a spin up and spin down, and also a positron that can have a spin up and spin down. So it is interesting that, really fascinating, by that Paul Dirac set out to search for a linear equation that is linear in derivatives for, let's say, some theoretical reasons, and discovered this equation that really describes electrons with spin, and concluded as well that you need necessarily in your theory particles that are the antiparticle of the electron. This is also can be found when you quantize this theory. This can be found in the requirement of causality and the propagator, the requirement that the propagation of particles is causal and doesn't transfer information. The commutator vanishes outside of the light cone, same as for the scalar fields that we discussed in the beginning of the lecture. That is also a reason why you would need antiparticles, but historically the antiparticles were found in this Dirac theory and had been predicted by Paul Dirac. Okay, finally we are coming also to the Lagrangian formulation of the theory. So I should tell you that you can get the equation of motion from the following Lagrangian, where you have I psi bar d slash psi minus m psi bar psi. So if we were to apply our variational principle, you will find that this d slash I d slash minus m psi times psi is equal to 0 is what you find when you apply the variational principle to this Lagrangian, and this is nothing else but the Dirac equation. Now remember the mass dimensions and the dimensional analysis. So the mass dimension of Lagrange density is 4, as we know. Now the mass dimension of the mass and the derivative operator is 1. what is now the mass dimension of the psi bar psi terms? By the requirement that the total mass dimension of the Lagrange function is 4, this product has to have mass dimension 3, which means that each of the fields has a mass dimension 3 on 2, which is a little bit unusual since we're used to work with even mass dimension fields, the scalars, but this is nothing wrong with it, and we really have fields with a mass dimension 3 on 2 here in the theory. Now we can do already some physical questions here. For example, we mentioned at some point the so-called four Fermi theory, where that was used to describe the weak electroweak force and the beta decay before people knew about the W and Z bosons. Fermi essentially postulated that there are 4 fermions interacting in this type of vertex, where there is a coupling strength that is called the G Fermi, the Fermi constant. And in Lagrangian, this would correspond to a psi bar psi squared term. Yeah, you have 4 fields coupled together. So now, could you already tell if this theory is renormalizable or not? And the trick is, or to check what is the mass dimension of this Fermi constant, as we know that things with a negative mass dimension, like something like gravity with 1 over mass dimension, would be non-renormalizable. So since we know that psi bar psi has mass dimension 3, that means that psi bar psi has to have mass dimension squared has to have mass dimension 6. Combining it with the requirement that the Lagrangian density has to have mass dimension 4 means that the Fermi constant has to have mass dimension mass dimension minus 2. In fact, it is roughly given by 1 divided by the mass of the W boson squared, which is really the mass of the interaction that mediates this vertex. When you zoom in enough, when you go to energies that are of the order of the W mass, you can really resolve the vertex and you see that it is not a non-renormalizable interaction, but an exchange of another spin 1 particles, which is called W or Z. But we will come to that later in general, what it means to have these wiggly lines of boson interactions in this case. Okay, so already our discussion of the Dirac, Lagrangian, and the dimensional analysis told us something about renormalizability of such theories like the Fermi theory. Now we can come to the question how to quantize the Dirac field, and we will not go through this due to the lack of time in such detail like the quantization of the scalar field, but we just discussed the general idea. And remember that for the scalar we had the Bose statistics, which means that if we have a 2-particle state with p and p prime momenta, and we exchange these 2 particles to have a state with p prime p momenta, 2-particle state where these particles have been swapped, we have a plus sign. So it's this swapping particles doesn't give you any additional sign in the wave function. And this is the consequence of the commutation relation that the creation and annihilation operators A and A dagger commute have a commutator that is proportional to the delta function in momentum space, and the A and A mutually and A dagger mutually have vanishing commutators. Now for fermions, the Fermi statistics is actually such that if we swap 2 particles in their place, you get a minus sign. This is very interesting because, as we discussed quite at length in the beginning, the fact that we have the Bose statistics and we can swap the particles without negative sign allows us to stack arbitrarily many particles in the same state. But for fermions, the so-called Pauli exclusion principle works. If we wanted to put 2 particles with the same state in a 2-particle state, the state would be identically 0 because it cannot give us a minus sign, or the only compatible solution for a state of two particles of the same type is that the wave function is just zero, it's the vacuum. Now, on the technical level, this condition is realized when a dagger A is equal to minus a dagger P, a dagger P prime is equal to minus a dagger P prime, a dagger P here, which means that their sum, right, bringing this to the other side, means that their sum is actually vanishing. And we have already introduced the notation of the commutator, that this curly brackets means that the anti-commutator, yeah, this is the sum of the components that have been swapped. So the anti-commutator for those particles has to vanish now. And the difference, it's not the commutator, it's the anti-commutator. Now, it also turns out that requiring a positive ground state energy forces us to introduce the following anti-commutation relations that we have, as before for the charged fields, we have creators of electrons, a dagger, we have the creators of positrons, the b dagger, and they mutually have an anti-commutation relation that is equal proportional to the delta function, the momentum space, same for the creation annihilation operators for the positrons, and their a anti-commutators, mutual a dagger anti-commutators, as well as the a and b dagger anti-commutators, they all vanish. Now, analogously to the Klein-Gordon equation, the fields can be decomposed in their plane wave solutions. As I said, they always have this plane wave exponential oscillatory term factor. There is the aforementioned u and v functions for the electron and positron spinors, and we have the a and b dagger operators for the particle and antiparticle states, for the electrons and positron states. This is really analogous to the charged Klein-Gordon field. And the rest is the same. We have the measure with the integral of all momenta and the sum over the spins as well, because we have always the possibilities essentially of a spin up and spin down for the spinors of each type. The electron positron spinor. We have in the dagger, we can apply the psi bar. We can apply the bar operation, multiplying it by taking the Hermitian conjugate and multiplying it by gamma 0 gives us the u bar v bars. So the bar operation really acts on this spinors here. We have also complex conjugation that acts on the exponential functions, and we get the bar dagger here, and the dagger here goes away on the creation and annihilation operators. So overall, those are the expanded fields of the psi and psi bar type, and the canonical commutation relations, anti-commutation relations, are now equivalent to the following anti-commutation relations for the fields. Psi at the equal time, psi alpha and psi dagger beta with an extra I factor are equal to the I delta in position space. And 3 is a three-dimensional delta function here. At the same time, their psi anticommutator and psi dagger anticommutators vanish from the fields. Finally, there's a conserved current. Actually, again, if we have symmetry, a global symmetry of the type that psi goes to negative I theta psi, where theta is some small parameter, and psi bar then goes to e to the I theta psi bar. We can see that terms of the type psi bar psi obviously are invariant, and since theta has no dependence on the space-time coordinates, also the d slash the psi bar d slash psi terms are also invariant under this transformation. Now the small, expanding the exponential functions here, the small perturbations of psi are delta for the psi field, the delta is delta psi is negative I theta psi, and for the psi bar field it's I theta psi bar. And we can use our Noether theorem to find the Noether current, which is the variation of the Lagrangian with respect to the derivative of psi times the variation of psi. We can plug in our first the derivative of psi, given that we have this following Lagrangian. The derivative of the Lagrangian with respect to d psi, d mu psi is, this term goes, and we have I psi bar gamma, and then this variation here, this small parameter, as we said before, is irrelevant, so we get like the negative I psi from the variation of the field, and in plugging this in, we get combined the Noether current, that is psi bar gamma from the first part, and psi here, where we have a negative I combined with the I just gives us a +1, and then we have psi bar gamma psi gamma mu psi, which is the so-called current of the the fermion current, the electron-positron current, essentially. Well, the conserved charge that is related to this is the zeroth component of this. So we have a gamma 0 psi bar gamma 0 psi. The integral over space, this gives the total charge, and if we were to write this in terms of the creation and annihilation operators, this is essentially the number of electrons, and this is the number of positrons. So the total charge in space is the sum of as the difference of the total number of electrons minus the total number of positrons, which is physically completely understandable. That gives the total net charge of a region in space. Well, that was it for now, and next time we should talk about making this symmetry space-time dependent. In other words, making this theta symmetry dependent on the 4-vector x, and we will see what kind of interesting and quite fascinating consequences this will have.